Hello everybody, this is our first actual lecture, Introduction to Computer Architecture. I hope everybody could watch the first video, Introduction to our course. You can access all the material in the Brightspace, all the videos. And it's really important because all the organization that we have for the course, I explain on that video. So here we're gonna start talking about giving an overview of our course and a little introduction to computer architecture. First of all, I want to talk about a little bit of the difference between computer architecture and computer organization. Those sometimes it's really common to see those topics in the literature. You can see a book that is about computer architecture and organization. So basically, architecture is all the attributes and operations that are visible to the programmer, and they have a direct impact on the logical execution. So how you're going to program your computer and which type of operations you're going to be able to do, that's the task of the designer of the architecture. And the architecture is defined by the instruction set architecture. That's a set of instructions and possible operations that you have available. And organization, on the other hand, it's the operation units and their interconnection. So, and the idea of the organization is how to realize the architectural specifications. For example, in the architectural design, we're gonna decide, okay, is this computer gonna have a multiplication operation, like in the CPU itself? And okay, after we decide, okay, this computer is gonna have a multiplication, the computer organization is gonna decide, okay, it's gonna be a multiply unit. So we have a CI, one unit for multiplication, or we just gonna do a repeated addition to provide the multiplication operation. So it's that's just like a topic that I want to talk about before, because sometimes there's a little confusion on computer architecture and computer organization. But let's talk about the typical computer. And so this is actually the von Neumann definition of a computer. Basically, we have a central processing unit, and in this processing unit we have the control, so how we're going to provide the instructions that we want to provide. We have a register file, that's basically a set of memory that's really close to the CPU that the CPU can access without going to any type of memory. And we have a data path and how the data can be accessed by the CPU. And at the same and here at the same, let's say, level, we have the memory that can be directly accessed by the CPU, right? Usually what we're gonna see in a couple of slides, the CPU basically fetch data from the memory, execute that memory, and write it back if it's required. And so these arrows that we have here, all of them are buses. So in this case, we have the memory bus here. We're gonna see that's not just one bus, but like it's a several type of bus to provide the memory functionality. But we also have I/O bus. This I/O bus, it's how the CPU is gonna talk to other input-output devices. So USB, that's going to provide keyboard, mouse, or any type of microphone that I'm using right now. So the hard drive. So sometimes you have a secondary storage that you have to use to store your operating system or your personal items. And actually, even the video card, sometimes you need another bus. Sometimes you're gonna have a express way to connect video to the control, to the CPU, so we can talk faster, but it's basically an I/O bus as well, to provide data from the CPU to the I/O devices. And so the CPU is actually a really simple device. Basically, we have this little so basically we have this little algorithm that the CPU it's always processing. So we have a program counter. It's a specific point in memory that our next instruction is gonna be provided from. So we have this, and if we don't do any operations with the program counter, it's just gonna add up. So we're gonna fetch the next instruction, the next instruction, the next instruction. Sometimes, if you have subroutines, you have to change your PC, your program counter to another position in memory. That's not the next one, right next one, but you get the idea. Like it's basically which position we're gonna process right now, which instruction we're gonna process right now. So the CPU has to load data from the memory. Let's say we have an array, or you have something that doesn't fit your registers, because the registers are really small pieces of memory. And you have to store data back to the memory, because you need to use this memory, this data after. So you have to store it back. So the PC, the CPU has to be able to store back to the memory. And you have to perform data operations, right? You have to perform logical operations, have to perform arithmetical operations. So the CPU has to be perform data operations on the so actually perform data operations on the register file is to store and retrieve data from the registers. Sorry, but of course that CPU has to perform operations as well, change the data that you have. And we can have additional conditional change to the program counter, so we can have loops, we can have subroutines. So basically what the CPU does is, while the computer has power, so you have the instruction register here, that's a piece of memory inside the CPU. We go into the memory, and we're gonna access where the PC counter is pointing in the memory. So this is our instruction. So we go into the memory, we're gonna access this address here. So it's a fetch instruction. We're gonna store this what's inside this slot of memory in the instruction register. After that, we're gonna decode and execute this instruction that's inside the instruction register. So in this case, we have like we're gonna see in a couple of slides, but basically we have a string of ones and zeros, and this string is gonna tell us which type of instruction, which parts of the CPU is gonna be accessed to execute that instruction. And after that, we have to adjust the PC. That will depend also in which type of instructions do we have. And so if maybe the PC is just going to the next instruction in the following slot of memory, you just increment the PC, or you have to change to another point in memory. And you're going to do that while the computer has power, and you just keep doing that. The CPU is just doing that. The memory, in the other way, we have several implementations of memory. And you can see the memory basically as a big array. And we have the static random access memory. This random in the name of the memory, it's more you can understand it more like the random access time. So for example, any point in memory has the same access time. Doesn't matter if it's in the beginning of the memory or the end of the memory. So this is what this random is. Not that you're accessing random points of memory. It's just because doesn't matter where your data it's stored. It's gonna have the same access time. And this is usually used to cache memory. So between the memory, the main memory, the RAM that we use, and the CPU, usually have a cache memory. We have actually layers of cache. One is smaller and faster than the other, because it's better for the CPU to have a really fast memory closer to it. There's a concept in computer science and computer architecture that's called locality. So usually when you access a piece of memory, you're probably going to access that piece of memory, closer pieces of memory from that one in a short period of time. So it's good to have a really fast, and even if it's small from the point of view of the main memory, to have a really fast and small memory close to the CPU, and that's the SRAM. A little different from the SRAM is the dynamic RAM. The dynamic name here in the RAM, it's more about the refresh rates that we have to have on this type of memory because of the technology that we have. Usually it's a slower memory than the SRAM. It is a slower memory than SRAM, but it's bigger, so you can store your operating system here. You can store big pieces of software here, so you can access them to in a way that the CPU can access the programs in the operating system that you're executing. And we also have flash memory. And usually that's used to firmware, so it's like a piece of software that you have that has to work really close to the CPU, but it's not the RAM. Yeah, so as I said before, random, it's about the same access time for any position. Buses, as we talked before, it's how the CPU is going to communicate with the memory, with the I/O devices. And it's basically a group of wires, so you can see that it's a group of wires that carry the signals between the components. So if you need, my CPU is 8-bit, I need to communicate with my CPU with 8 bits. You have 8 wires. That's the bus to the CPU, for example. That will carry the signals, the electrical signals to provide that functionality. So you have several types of buses. You have the North Bridge. Usually the North Bridge is the component that is closer to the CPU and connects the CPU to the memory. And you can have sometimes you can have the PCI Express here connected to the North Bridge, so you have a really fast way of your video card to communicate with the CPU. You have the South Bridge. Usually South Bridge is connected to the North Bridge. So the companies, they are gonna use their own names for those bridges. So Intel is gonna use their names. The other company is gonna ARM is gonna use other names. So basically, what we have is that the South Bridge, there is another component that's connected to the North Bridge. So when we have several pieces of I/O connected to the South Bridge, and this South Bridge is connected to the North Bridge that's connected to the CPU. So it's just a better way to design and focusing on what's faster that can be accessed with more priority. So we have PCI and PCI Express that is usually is used to video cards. So you can have a video cards connected to the computer. So you can use monitors, and nowadays you can process huge amount of data with for deep learning algorithms using video cards. They're going to use this because you can send like arrays and matrices that is going to be first the communication from the CPU to the video card is really fast because you communicate whole chunks of data, and the video cards it's made to process matrices. So that's the idea of using video cards to process AI and deep learning algorithms. You have SATA that's usually used to the secondary storage memory, hard drives. SCSI is another one that usually is used to the secondary storage, your hard drive. USB. So USB, it's everybody knows. So it's everything that's connected, temporary, removable devices. It's connected through USB. And there's this old one that's PS2. Usually they were used to connect the keyboard and mouse, but nowadays probably you're not gonna see it. Only if you have a really old computer, you're gonna see it. Keyboard, mouse are Bluetooth and USB. So I/O devices are any component that is not the CPU, the memory, or a bus. And usually we need an interface controller to talk to those devices, right? So your CPU, it needs it needs to talk to a controller to talk to your device. So video cards, sound cards, hard drive controllers, network, Wi-Fi, Bluetooth, Ethernet. And I/O devices can also use interrupts. That's in a way, because sometimes you can imagine that the CPU is really fast and the I/O devices are not that fast. So sometimes your hard drive has to fetch some data and it's pretty slow. So what they're gonna do, okay, you set an interrupt, and when this interrupt is raised, so when you have a high signal on that interrupt, and that's on that port, you can, okay, the hard drive is ready, so I'm gonna read the data from the hard drive. It's something like that. We also have some other interfaces called, for example, DMA, that breaks a little bit this logic of memory CPU, because you can have some devices that has direct memory access, the DMAs. So what they can do is just, okay, I'm not gonna wait for the CPU to store this memory. I'm just gonna access the memory myself and store pieces of information there. That's something that's possible too. So we're talking about the CPU and how the CPU communicates with the memory. So basically the CPU has to store and retrieve data and instructions. So the address bus selects the word. So you have this address bus. Remember that the memory is just a long piece of, it's a long array, but we can access any piece of this array with the address, with the correct address for that memory. So the CPU sets the address bus, and we have this data bus that's two ways. So we can go and store memory, we can retrieve memory, we can fetch memory from the memory array. And we have a clock signal, so we know when to start our communication. And we have a bit. Usually we have a bit to indicate if we want to write or to read from the memory. So you set the address bus. Oh, okay, I want to read from this address, and you set the read write. You set this bit to 1 because you want to read. You push the clock and request that read, and you wait the line here to be ready with the data that you required. And if you want to write, you just set this to 0. You have to set an address to write to, and it's the same. So in this case, the CPU is going to provide the data to the data bus. So the memory structure usually it's basically it's based on words. So a size of bits that's stored in memory, it's the word that we're gonna use. So it's a one-dimensional array of n bits equals to one word. So you can have a 8-bit, it's a byte. It's really a common size in some types of computer. Nowadays you have 32 bits, and you can locate at 2 to the power 32 minus 1 words if you have an address of 32 bits, the same way that we have. And sometimes, because for example, if you have an address of 32 bits, you can locate this size of words. But if you have a bigger memory, how are you gonna do? So you need memory management hardware to access more addresses than this number of bits that you have here. And basically this is the idea. So it's a string of bytes, and you have like 0, 1, 2, 3, and n. For example, if it's 8 bits, it's 8 minus 1. So this is the bit number 7. This is position number 7. Yeah, so basically the user view of computer systems is you have the instruction set architecture here. This is the hardware definition, the operations that's available. And basically it encodes and behavior of the instructions executed by the machine. After that, you have the system software that's going to communicate with the hardware, and on top after that you can have your application software. That's usually what you're going to see when you program, when you use your command line. You're going to be in this layer here. Some common ISAs are x86 Intel AMD, so for PC and servers. That's really common instruction set. Most computers are use this instruction set. The ARM, so you have for the ARM you have several types of instruction sets depending on the version of the ARM. We're gonna see that later in this course too. MIPS, it's for embedded systems. Usually you're gonna see that in small computers, small devices. And AVR, that's 8-bit microcontrollers. This one is really common for Arduinos or other types of microcontrollers. So most programs use a high-level language. So you're gonna use C, you're gonna use Python. Actually, Python and others is bytecodes, but it's a high-level language as well. The machine code is responsible for all aspects. So the machine code is the one that's gonna fetch the instructions, the instruction placement, the data interactions, and how you're gonna encode the instructions. And the assembly language, it's a closer machine code representation. Usually you have a one-to-one mapping between the assembler, the assembly instructions, and the machine code itself. So you can see that it's basically a high-level language like C to an assembler that's gonna be the choose the building blocks that you have, to the machine code that the CPU understands. And virtual machines, for example Python, Java, usually you have this high-level language and it's compiled to bytecode. So those bytecodes are executed by virtual machines, and these virtual machines that communicate to the machine code. That's a different approach to the problem, but basically you always need several steps between your high-level language, something that you can understand, everybody can understand, and the machine code. Yeah, so for example, you have a code for swap integers here in an array, and we have the same behavior here in assembly. So basically you create a function, you have a function here, you have a position. And what I want to show you here is that we are using registers. For example, this IP here and this R2 here. Those are the registers that we're using to do the stamp receives V in the K index and everything. So that's how we do the swap. So we select some registers in the CPU, and you can use those registers to save the memory while the CPU is doing. And after that you can move, for example, you can use you provide this subroutine, and you can move the program counter back to where it was before, and you just did the swap operation. And that's the same with C. So you have a function here that do the operation. You just call this function whatever you want, and use and there's not a one-to-one mapping to this, but from this to machine code we can have like a one-to-one mapping. And basically computer architecture and computer organization are it's basically managing levels of abstractions, right? So we have the physics. That's basically how the electrical part of the computer is going to work. So we have the electric fields. That's Usually we use some memories in the past. We still use some electric fields for capacitors and everything like this in memories nowadays, but the bit that we saved was in electric fields in the past. So the physics level is the electrons and atoms and semiconductors that make our computer work, the electric signals. And we have the device level, that's the MOSFET, so that's used by the chip manufacturers. We also have the analog circuit, transistors, capacitors, resistors that need to control and in embedded systems, they do the time analysis. And with using these abstractions here, abstracting these levels here, we have the digital circuit. So we have the logic gates that we're gonna see in the future classes. So it's the components used to build the digital system. So the AND gates, the OR gates, the NOT gates. And on top of this, we have the logic, the Boolean algebra that's used to do the operations that we need, the addition, the multiplication, to implement and design the digital circuits. So we use this as we are using all these levels here, but we are applying that to Boolean algebra. We simplify with K-maps. We can do truth tables, but we abstract all these levels here. And in the microarchitecture, so the adders, the muxers, the registers, we have a microarchitecture that use the Boolean algebra to implement the low level, the micro level that we required. And on top of that, we have the instruction set architecture. That's the interface between the hardware and the software, the operating systems, and that's it. And that finishes our introduction class. Thank you, everybody.